The broadcast is now starting. All attendees are in listen-only mode.
All right, today we're going to be talking about modeling water demands, and it will be, for the most part, focusing on um, what you might consider municipal water demands. But most of what I'll be showing you is really about how to use uh, scalar and vector data in a gold sim model and organize the model. So hopefully this is useful for those of you that might not be doing exactly municipal water demand, but I think it will be a good refresher for those of you that are building any kind of um, water balance model, but even not even in the realm of water balance, just because I'll be talking about a lot of pretty basic stuff. But unlike the previous models, most of what I'll do today will be built from scratch. Now, because of our limited time, I will be building this model fairly quickly. So if you get lost, please let me know. But also, you can watch the video recording afterwards. Okay, so in this model, I'm calling it water demand model. What I want to end up with here is given some population data, which you see over here in the spreadsheet. I have just a very simple table here of population data for 3 different cities that happen to be in the area close to where I live, followed by per capita demand based on based on the population. You can then calculate water demand by multiplying this per capita demand by the population, but it is split up into indoor versus outdoor demands. What we want to do, well, the assumption is that the indoor demands are constant over time, and the outdoor demands will have a seasonal pattern applied to it, which is defined in this table here. Okay, so, oh, and by the way, these numbers are assumed to be a factor that, when multiplied by the outdoor demand, that they would represent the monthly averages for each of those months. Okay, so I'll go ahead and start now. The first thing we want to do is specify population. And so I'll just go ahead and start with the data element, and I will make this, well, first of all, I'll call it population, but this actually represents today's population. So I will put initial here. Boy, I'm having trouble with my keyboard at the moment. Not sure why. Okay, it'll have to be that. All right. The next thing I want to do is add a unit of people, or in GoldSim it's called PERS for persons. We had to shorten it because we wanted it to be consistent with other units that we might want to convert. For example, if we want to look at 1,000 people, so these numbers over here in Excel that are shown in thousands, we can have a unit that would allow us to specify 75, with the unit being 1,000 people. And so that's a built-in unit that we have. And if you look at our units, let me just show you that real quick. In our unit database, you'll see that the persons units are under the items category. And in there, you'll see that item is the same. It's defined in the same way as person, only because these kinds of units are not like the other measurement type units. They're really just items. So GoldSim doesn't actually know the difference between an item and a person. Just keep that in mind. But it does know the difference between K, PERS, and PERS, right? It knows that K, PERS is 1,000 times more than just one. Okay, so that's important because then we can, if you're plotting, for example, you might not want to have all these trailing zeros, especially when you're in millions. So you might want a different unit. Okay, so I'm going to specify KPERS as my unit, and then what I want is I want to specify these numbers for all the different cities that I have. So I'll go ahead and click on type to change the data type from a scalar to a vector. Then I want to create a new array label set, but I've already done it. But let me just show you how you would create it. Go to create and then add new, and then you would create a named set. And when you do that, you get something like this. And I just went ahead and copied and pasted the labels into here, which is what you could do if you had a large set. Okay, so I have those cities there, and now that it's set to be cities, as soon as you do that, you see the input field goes away, but then you can click on edit data to edit all of the values. And I just realized something that I have something left over from this morning, so we just need to delete. That was scenarios. We were looking at that at the end. We will again if we have time. Okay, so I just come over here to Excel and copy the values and paste them in. You'll notice, by the way, because of the display unit that's set there, when I go back in to see them, you'll see the GoldSim already appended the units to those values. The reason that it does this is because there's a chance that you might change the display unit, and it would need to know what those equivalent values are for that display unit, just so it can do a conversion for you. Okay, so that's our initial population. The next thing I want to do is I want to have two separate calculations, both one for indoor demands and the other one for outdoor demands. Okay, and because the, and by the way, I put the model browser over here just because I need extra space on my screen for this presentation. Typically, I would still have it docked over here, but I just need to have extra space, so I moved it. Okay, I want to localize these containers, and the reason for that is because the calculations inside, well, there are some similarities, and I would prefer not to have to call all of my expressions indoor something something, outdoor something something inside of here. I just want to call the calculations, assuming already that we know we are talking about indoor versus outdoor. So I'll show you what I mean more when we go in there and start working. Okay, so those are localized. And now I can go into indoor and work on that. Okay, so the indoor demands is just a very simple calculation of the per capita demand. And this, by the way, this unit here, kind of a strange one, gallons per capita per day. And so we need to make sure that we have that unit. Well, we don't have to. And let me show you what I mean by that. Let's say that we have a data element here that represents the indoor unit demand. And I don't actually need to call this indoor unit demand because I am in the indoor demands container. But to make this a little bit more clear, I will just call this indoor demands. And I always like to put on every single page in my model, I like to have bold and 16 font. And then I also like to have a small description right underneath that in every case. Okay, so we will call this unit demand. And I'm also going to have another unit demand input for the outdoor, but I can name them the same thing because these are in localized containers, which is nice. Okay, so in here we want to have a unit that's called GPCPD, gallons per capita per day, or if you're using metric, you would use maybe equivalent to that in metric. But this would be a custom unit, and I built it this morning for the morning webinar, but I'll just show it to you. If you go in here to Flux Volume, expand that, you'll see that this is the added unit that I put in, a custom unit, but still based on the SI unit of, it would be liters. It's actually just liters per second is the SI. People is ignored in GoldSim, unless you're talking about a conversion between 1,000 people and just people. But anyway, this right here is the custom unit that we can then put into our element here. Okay, and now I do also want to make this a vector, just like I did before with the population for the various cities. And I'll copy the values from Excel and paste them here. Okay. All right, so now we have the unit demand, and the next step here is to calculate the demand based on the population. So I will create an expression here and call this indoor demand. I'm going to call it vector because I'm also going to sum them for all the cities and calculate the total demand. But I don't need to actually say indoor, right? So I can just say demand vector, and then I'm using CFS. You can use any type of flow unit that you want, just using CFS, cubic feet per second, in this example. All right, so I'm going to change this to vector and vector of cities again. And now I just refer to the population and multiply that by the unit demand. And that will give us a flow rate per city. These are going to be constant values because the population is constant right now and the unit demand is constant. Okay, so now we can calculate the total demand. I just made a copy of this element here. This total demand. Okay, and now I want to sum the vector. So I will make this a scalar because when we sum the vector, it becomes a scalar. So this is a built-in function. It comes with built-in. So if you right-click in here, go to functions, and then array operators, and you will find sum. Then we just put in the demand vector, and it will tell us the total demand. Okay, so that is pretty much it for the indoor demand. It's pretty easy. But what I want to do is I'm going to keep this, but then add to it for the outdoor. So I'll just Control A, Control C, and then, by the way, to browse in the model, I don't know if you know this, but you can click on these to browse into different containers immediately. You can just click on these drop arrows right here in the browser or in the address bar and go to the other container. Now I'm right inside the other one. Paste, and then just change a couple things. All right, so the unit demands for outdoor, and I'm going to omit some descriptions just for the sake of time, by the way. We shouldn't do that in the real model, obviously. Okay, so I'm pasting these in, and go to that point. And then for outdoor demand, there's quite a bit more going on here. We have this demand pattern here, and I want to apply that to this average demand, so that we can come up with a seasonal a value that fluctuates over the seasons or over the months. So I'm going to need a table, and I will just call this this table, I guess. I'll call it seasonal pattern, I suppose, is a good name for it. I could use either a lookup table or a data element. And I'm trying to think of what might be a better approach. Kind of feeling like I think I might use a lookup table. I used a data element this morning, but let's go with a lookup table. Seasonal pattern. Okay, and what we have here is these values are unitless, so I won't have any units here. And we will be referring to month in the rows. So I'm just going to give it a label of month, and then go to edit data. Now I can put the values in. What we have in the lookup table, however, is an indexed-based monthly value. So I just need to put these numbers in here, and then copy and paste. Oh, I just had a realization. Because I also want to include a spline interpolation, it is actually going to be easier right now to use a data element. Sorry about that. That's why I used the data element. I just remembered. Okay, so I'm going to make this a vector, but this will be a vector of months. So similar to what we just saw with the lookup table. But a little bit different. Okay, so forget what I said about the numbers. We'll just copy the values and put those in there to associate them with each of the months. Okay, so now that we have the table there, now what we need to do is calculate I'm going to call this a normalized pattern, because what I want is for the average of these values to be 1. But what we could do is, for example, we could just quickly, if I change this value, what I want is I want all of these values to be relative to each other, but still come out in the end with an average of 1. So in order to do that, we need to normalize these values with another expression. So I'm going to do that now, and this will also be a vector of months. I'll call this normalized pattern. So the reason I'm doing this is just to make sure that we still end up with the same average annual demands is the reason I'm doing this. And you could set up the numbers to make sure that happens, but I like to do this just so, just in case somebody enters a value so that it gets it off so that it doesn't add up to an average of 1, then this will fix it. Okay, so to do this, first we, again, make this into a vector of months, because we want it to have 12 values. And then we just refer to the seasonal pattern and divide it by the mean. This is another built-in function, mean of the vector of the seasonal pattern. So divide it by the mean to get it into a normalized set of factors that then we can multiply by the demand. Okay, so now we can create another expression and call this we'll call it the, pattern on a monthly basis. So these numbers will be constant over the course of each month. And it's probably a good time right now to talk about the simulation settings that I have. So what I'm going to do is I'll run a model on a calendar basis for a future scenario. In this case, next year, just for 1 year is all. Okay. And I'm just going to run a single realization for now. Okay, so that is to get the normalized pattern. Then this will be a number that changes over the months rather than a table of 12 numbers. Okay, so this is just a table, right? This is also just a table. It's a vector. They're constants. What I want to do is convert that table of constants. So for example, when I run this model, you can't look at a time. It doesn't make sense to look at a time history. It's just a table that looks like this or like this. That's all it is. It doesn't change over time. But I want to convert that to a time history that changes over time based on the built-in run property in Goldsim called month. So I'm going to open up this expression here and simply refer to the normalized pattern and then put in a bracket with month. Now month is this is a built-in run property of Goldsim. If you ever have questions about what are the built-in functions of Goldsim, simply just type the tilde symbol, which is shift, and the key above your tab key on your keyboard, and then just start typing. In our case, month is the one we want. And once you do that, you will now see that we have a seasonal pattern right here. And just to kind of play with this, to show you for an example, we could, let's say we want to, decrease, no, let's say we want to increase this May factor just a little bit. Now again, these are all relative to each other. And so I'm not going to really focus on, I'm just going to change this to 1.1. I'm not going to focus too much on making sure that these numbers averaged one. Rather, I will just rely on that normalized pattern. Okay, so when we run it, then you can see it changed the pattern a little bit. Now, there can be a problem. This might be fine to just use this pattern and go with it. And so in this model, I'm going to allow you to use this, but then have an option where you can say, actually, no, I'd rather have an interpolated form of this pattern. If you have a 1 month time step, obviously it doesn't matter, but we have a 1 day time step in this model. And so we're holding a constant value for the course of a month and then suddenly jumping. And if your model is sensitive to these, to this pattern, or to, I should say, outdoor demand, you could have an artificial impact to your model with these big jumps right here. I've seen it before, and it can cause problems in the way your model is operating unexpectedly, and it's really just because of this artificial thing, which is not really how it works, right? It's really it's actually changing. It's not even constant over the month, right? It's changing all the time. But the point is, we don't have these artificial jumps, so we want to then add the option in this model to do an interpolation, and it turns out that we have, I'm just going to move some things around here. We have a model in our library that can already handle spline interpolation. And ahead of time, I've already got it into a container, but I'm just going to copy and paste it into here. Okay, so this is spline interpolation. Again, you can get this from our website. If you go in, you'll see this, pretty much this is what you'll see when you download this model from our library. And what it requires is a vector of monthly values here as an input, and then it will output the time series of the spline interpolation. So if I, and also you just need to link the table to this expression. So if I open this up, you'll see that it's already linked to normalized pattern, just because I set it up this morning in this morning's webinar. But this is just referring to the normalized pattern. So if I go back up a level, you'll see that normalized pattern is then sent into the spline interpolation. So that's where it's going, is right into here as a table. Then we do some things here that then will then output a time history, which is what we want to use as the seasonal demand pattern. Okay. Oh, by the way, we also put some. Let me scroll a little bit. We put some checks in here. Let's see if I'm actually going to move that over a little bit. Okay. We put some checks in here just to make sure that you still end up with the same total at the end of the simulation as you would if you were just using monthly averages. So that's just a way to check that. Okay, so now I will have another type of pattern that's not constant over the months, but instead interpolated with a spline interpolation. So I will call this pattern spline. And then what we want this one to be is referring to the output of the spline interpolation. So I'll just say spline interpolation dot output, and then it refers to it. So spline interpolation output is the equation. So that's the element inside of here called output. So I'm just going to go in there. That's this one here. Okay. So let's see. It might be nice to compare the two patterns. So I will put a time history here that looks at both pattern monthly and pattern spline. Model. And there's the comparison between the two. One other thing that you might want to do is not just create a bunch of charts that say history with a number at the end. It doesn't make a lot of sense to do that. So I will call this, let's see, seasonal demand pattern. And then these labels are kind of ugly down here. So, and it's obvious we're talking about a seasonal pattern. So I'm just going to call one monthly and the other one spline. So it's nice that you can customize the labels for your chart. And so now we run the model and look at the chart, and we see this with in the legend we have the monthly and the spline. Now this side over here, you see it says monthly. That's just because it grabbed the very first label. So we need to modify that. So I'll go here to chart style and go to y-axis, and rather than use the label that comes with the first item that you have, the first output, I'm just going to change this to, actually I'll just take it out. We don't really need anything there. That's fine. Okay, so now that we have that, this is something we could apply then to our population to get a demand that is seasonally fluctuating. But we need a way to choose between this option or this option. So to do that, I'm going to use a selector and a data element. The data element is going to be a conditional output, or a Boolean, that is essentially just going to tell us whether to use the spline interpolation or not. So I will, there are a couple ways to do this. One way is to just say spline on like that, meaning it's using the spline interpolation. That's probably a fine way to do it. Then we want to change it from a value output. It's not going to be a number, it's going to be a condition output. So then we change that, and we want the default to be false. So by default, the spline will not be on, and it will use the monthly average values over time, since this is set to false. So then we come over here, add a selector, and we will call this seasonal pattern. It's the ultimate pattern that we'll be using. And then we come over here. Oh, I'm already using it. Where am I using it? Oh, I'm using it up there. Okay, so for now, I will call this seasonal pattern table, I guess, and then come down here, and now I can use that name. Okay, so what I want to do with this is just put the conditional output right there in the if statement. So if the spline, whoops, I didn't mean that. If the spline is on, then refer to pattern spline. Otherwise, pattern monthly. So some of you might be tempted here to say if spline equals true, but that is a redundant statement. We don't need it because the output is a Boolean already. So that wouldn't help us. In fact, well, it's the same. It would be the same to do either way, but might as well just give it a name that makes it very clear and just leave it at that. Okay, so now we have the spline on, and now we could, for example, have a dashboard with a checkbox. I'm not going to do anything fancy with the dashboard. I just want to show that you can have a checkbox that is linked to your Boolean of spline on. So then we can come on here and we can say spline interpolation question mark, and by default it will be unchecked. Make that a little bit bigger. Okay, so then in your model you could say, is it interpolated or not? And not only that, but we could say, well, I don't want to compare these two options. I just want to display the one we're using. So instead of linking to these two, I will just seasonal, or just link to the main output there. So seasonal demand pattern, and then we can just keep it like that. That's fine. Okay, so now what I can do is go into my dashboard and add a result chart that links to that table. So I link to the table, or link to the chart, and I'm going to show the header and show the well, let's see, the y-axis does not need a title; it just needs values. That's probably good. So now when I run it, you see we're using the monthly values, and then we can check the box. Try it again, and it shows the spline interpolation. Okay, so that's good. Now that we have that, now what we can do is just apply the unit demands to our pattern. I'll put that over here. I'll put all this over here. Okay, there. Okay, so the last thing we have then is going to be it's going to be a demand, total demand, multiplied by the seasonal pattern. But I think what might be more useful is to see what the demand is for each of the cities by applying all of them to the seasonal pattern. Okay, so let's see. I'll just create a new one. I'll call this, what do we call this other one? Demand vector. Oh, you know what? We just need to modify the demand vector, actually. So the demand vector then is just going to be the same thing we did for indoor demand. And notice how I didn't need to change this equation at all. It still refers to the unit demand in here for outdoor demands. Then we just multiply it by the seasonal pattern. That's all we need to do. And then it'll have the demands for each of the cities with the seasonal pattern applied. Okay, and then we can also have the total demand if we want to see that. And if we run the model, then we can look at, and also, because this is a vector, this element right here called demand, the demand vector, because it's a vector, by default, it's not going to include the time histories. So that's what GoldSim does when you change an output to a vector type, it'll turn this off just because it could be a large vector, and we don't want to save everything by default. We'd rather that you choose what you want to save and assume we're not saving it until then. That way you don't have models, you don't bloat the model too much. Okay, so then we add the demand vector. And when we add the demand vector, you see that it shows edit over here, indicating that we have multiple items that it's going to plot, and it will do that for each of the cities. And since it will show these cities in your legend on your chart, then you don't need a label here. Okay, outdoor demands. Run the model, and there are the 3 demands. Okay, so now we have that. The next part of this is, well, the first thing we want to do is go up a level and then just add the 2 together so that we have a total demand of indoor and outdoor. So I'm going to add a sum element, and I will just call this total demand, but I want this, I'm going to apply some other things to this. So I'm just going to call this, let's see, I'll just say raw demands. I don't know a good way to say it. But again, it's going to be flow units. And now I just add the indoor demands and the outdoor demands. You know what? I've decided actually I would prefer that this total is for all the cities still. So I'm going to change this to a vector again, vector of cities. I still want to see this information by city. So I'll delete that and go back to indoor demands, and I want the vector of cities. Same thing with the outdoor demands. Demand vector. Okay, so this is a vector of cities. And now what I want to do is, oftentimes when you're looking at demands like this, you will see that they're, if you, for example, did a mass balance or a water balance, and you compared your modeled demand to what actually was metered, perhaps your numbers are low. This is often the case because there are other things going on, like leakage in the distribution system, for example. And so you might have a fraction that you want to apply that will account for leakage. So I'll just put a leakage rate in here. And of course, this could be a negative or a positive, depending on if there's infiltration coming in or leakage going out. I'm just going to assume it's all out right now. And this number can vary, by the way, based on data from a lot of systems in the US. It can vary from 5 all up to 40% in some cases. I'm just going to say 10% loss right there. And another one that's often applied is the error, the meter error. And so, for example, you might you might get your per capita demand information from meter records. And so then when you finally apply it, you might end up with a number that is lower than what they actually delivered as a sum total. And that could be because as meters get older, they tend to under register sometimes. So we might want to add another one here, and I'll call this meter error. I'll just keep it also at 10. Well, no, I'll say 5. Okay. So now that we have those, now we can calculate the demand with losses. And so this will be a similar process. We just add another expression, demand with losses, and again, CFS and vector of cities. Then we take the total demand, and I'm just now going to multiply the factors, which in this case is going to be 1 plus the meter error plus the leakage rate, like that. So we've scaled this up based on those losses. And then there's one more thing, and that is the peaking factor. So if we were to look at, in fact, I'll just put in a new chart here that's called water demand plot, demands with losses. Put that in here. Okay, run the model, and here are the total water demands. Now, this is realistic for like on an average basis, but in reality, you would have some noise in here, and so you can choose to add that or not if you want it. There is some research on what those kinds of peaking factors might be, and if you needed to know, like for example, what's the highest water demand that we're going to see on a daily basis and throughout the year, for example, then you might want to apply a peaking factor. But I'm going to do it with a stochastic because it's not going to stay high at that peaking level for the entire year. Rather, sometimes it will peak and sometimes it will be less than the average. So I'm going to use a stochastic to define that. And in this case, I'm just going to do something quite simple. I'll just assume that it's based on a log normal distribution, and I will call this peak factor stochastic. And then this will be unitless, and I'll assume it's the same for all the cities, so it will be a scalar. And then I will come in here to the distribution and change it to log normal. I'm only using this just for ease because I only have to add the mean and the standard deviation, and I already know the mean is 1 because it's a multiplier, and I want it to average out to 1. But I'll put a standard deviation of 0.2, let's say. Well, let's say 1. Say a little bit less than 0.2. So a pretty small standard deviation, but you can see here that it's peaking at around a little bit more than 1.5. It'll go all the way up to 2. In fact, you can find out what the probability of 2 is. Go to the calculator down here and put 2 in, and you can see that the cumulative probability there is very, very close to 1, meaning that it's very unlikely that it would hit all the way at 2. If we put 1.5 in here, then you can see it's still pretty unlikely that we're going to hit 2, but it can happen. Every once in a while, it's going to happen. So that's kind of the idea of how you might see that. Okay, the next thing I want to do is resample this because it's changing every day, right? So I'm going to resample this every day of the month. And also I'll add some autocorrelation because it won't be totally random from one day to the next. It's probably somewhat a function of the climate or the weather. So you could have a few days in a row that where it's sampling high, and then followed by a few days in a row where it's sampling low, for example. So I'm just going to put 0.75 as kind of a medium high autocorrelation. What this means is it's correlating where it samples in the distribution to the previous day. So it allows you to give it some memory to the previous day and sample similar to that or correlate to its sampled position on the distribution. All right. So now that we have that, now we can apply the demand peaking factor. So I'm just going to copy, because I want a vector of cities again. But this one I'll call demand peaking, I guess. And then all I need to do is multiply the previous one, which is demand with losses, by the peak factor stochastic. And then we can compare the average demand over time with the one that has the peaking factors. So now I will add the demand peaking. There we go. And I'll just call this, I'll just give it a letter P so you can see the difference. Now we'll run the model, and oops, the colors are the same. I'm not really going to keep this chart. I just wanted to show you how with the peaking in there, how it compares to the average. And so you obviously want to do a little bit more investigation into these values, whether that's realistic or not, to spike in this way. You can see the flows are very high there. In fact, that does seem a little bit odd how high those numbers are. Let me see what these numbers are in here. I think I know what the problem is. Yes. Okay. So I forgot to change these numbers to be 1,000 people. That's a lot of people. Okay. So let me just change these numbers. There we go. Run that again. Okay, so these numbers look a lot better. All right. Then what we can do is run the model for multiple realizations. Run it for 100 realizations. And now what we can see is that if, for example, if we wanted to look at the range of demands for one of the cities, then we can see it like this. Or we can look at a statistic, which does also allow us to compare the different cities, because the statistic is only one line, so that allows us to compare different outputs. If you look at probabilities, then you can only look at one output at a time. But anyway, we can see that if we run more and more realizations, the average over time, or the average of all those values gets closer and closer to the average that we already calculated, which makes sense. But if you look at a single realization, you can see it's fluctuating quite a bit from one realization to the next. Okay, so now that we have that, now what we can do is look at changing population, changing over the years. So for example, what if we wanted to run this for many years? And also, by the way, we probably want to have the total demand or the sum of all the demands here on the end. So I'll just add one more expression. Sum of the demands. And then I'm just going to use the sum B. There we go. Okay. So if we wanted to look at population as it changes over time, then obviously we're going to be looking at a multi-year simulation. So let's go ahead and change this. Let's go with 5 years. Well, let's go a few more. Let's go to 10 years. So there's 10 years. And because we're doing some calculations to calculate the future popular model, the future population, I will now add a container for it. This, let's see. Yeah, it's probably okay just to call this population, and then I will localize it and put that in there. What you're going to see when I do that, oh, let me see. Hold on one second. There we go. If you move an item into a localized container, you'll see that the references will break. Let me just do what I just did over again. Okay. Right now, there's elements in here that are looking at this name, population init. Okay. If I move this into here, everything's fine. If I localize this container, it will all be fine. But if, go back, if I localize this first and then move this into there, GoldSim's not going to know where this name is anymore, called population init, because it's now become population init. So what that means is if you're moving things around like this, you should and if you want it to be a localized container, the best way to do it is to keep it global first, move the stuff in, and then localize it after. And what you'll see here is that GoldSim will automatically expose the output that you're using here in these other places. So in the exposed outputs tab, you'll see there is the exposed output that we're now using. By the way, GoldSim does not expose all outputs of these containers by default. Here in this container, we have many items in there. And if you go to the exposed outputs, you see there's only one output that's exposed. So GoldSim will not know out here about any other outputs inside there. We don't care, but if you did, you'd have to expose them. It's very easy to do it. And it does it automatically when you link by referring to those outputs that are in there. But when I go in here to population, now I probably want to do the same thing as I did before with the title. So I'll just copy, go in here, paste, population. And then since the container is already called population, it's redundant to say population again. So I'm just going to say, initial. And that might not sound like too great of a name in there, but when you go to where it's being used, it'll say population.initial, which makes sense, right? So it's good to make use of localized containers. It helps with your equations. Okay, so here's our initial population. And now what I want to do is I just want to copy and paste from another model that I have, a very simple calculator that uses a table, a growth table, a growth rate table, I mean. So let me just move these things over here. Okay, so I have an annual growth rate table. And what this is based on the year. This is based on calendar year. I'm not so sure that that's not always the best way to do it. You could also do elapsed year, so that no matter what year you decide to simulate, this table will always provide values for that duration. However, these numbers are probably associated to a real year. So in that regard, it's probably best to use calendar years. Just be careful with this, because if you change the simulation settings, then you might be out of bounds of this of those years. But I'm just going to use these for now. I think we go to 2031. Is that right? Let's see. We do. Okay, so we need to first of all set up a way to handle a situation where we're out of bounds. And we will go out of bounds in this simulation. We're going to go to 2031. So what do? One idea is to extrapolate, and we just do a linear extrapolation from the point before going forward. And if you're okay with that, that'll work. Another way to do it is to force it to not extrapolate, or if you don't expect it to ever go outside the bounds and you don't want it to, then I would change it to fatal error, and then the model won't run all the way. If it hit, it'll stop running if you hit the go outside the bounds of the lookup table. I think extrapolate is fine for now. Okay, so then what we do is from that point we can calculate this over here. calculate a unit growth rate by referring to the year, and then we multiply the population that we're keeping track of over here, and the population that we're keeping track of, by the way, has an initial starting point, and that's the initial that we had before. And now we have a problem because this is by city, right? Population per city. So we need to change this to a vector of cities. And then we need to do something about this growth rate. So how is it changing? Well, do we want a different growth rate for every city? Probably, but for this very simple model, we're not going to do that. So I just want to have a vector. I'll just create a vector on the fly of growth rates that are all the same for all the cities. So this is another built-in function in GoldSim called vector, and it will just automatically build a vector for you. So now we have a population, and instead of calling it population, because the container is called population, I'm just going to call it current. This is the current population as we are walking through time in the simulation. Okay, so now when we go into calculating the demands, instead of referring to the population initial, I want to refer to the current population. So that means we need to expose the current population output on the container. So to do that, click on the output port, go to current, right-click, expose the output. Now when you go to the exposed outputs tab, you'll see that it says current there as one of the outputs. Then we can go in here, instead of calling out initial, just start typing current. There it is. Population current times the unit demand. Then we go into outdoor demand, and where is it? Over here. So current population. Okay. Now we run the model, and I have a problem. Oh yeah, the growth has to be a vector. I forgot about that. Because they changed everything to vector inside of here. Let me see, what am I? Oh yeah, we changed it to current. That's right. Usually GoldSim will change these names for you, but because we had a break here because it was in the vector, it didn't pick up on that, and it didn't add that. Let me see what else we have. What other problem? Oh yeah, okay. Well then we don't need to add a vector because it's already a vector. Sorry about that. Okay, so let me just review what happened here. These used to be scalar outputs. We needed them to be individual for each city, and so that means we need a growth rate for each city because it is a function of population of the city. And the current population is also a function of that rate. So this is a feedback loop here. This is actually a positive feedback loop. The higher the population, the higher the growth. Okay, let's try it again. Okay, so this is running 100 realizations for 10 years each on a daily time step. That is a lot of data. But you can see here, going through time, you can see there's a slow increase over time. That makes sense. But another thing that you might want to consider in this model is that we might have an uncertain rate. These numbers are not set in stone, right? It may be 5 and it may be a little bit different. So you could put some uncertainty on those, and that would then generate a probabilities. Right now it shows a pretty consistent growth there, but it would be very easy to add an uncertainty factor on that growth rate, on this unit growth rate here. So for example, we could say this is the average growth rate, and then just put in a stochastic that is called unit growth stochastic. And this has units of percent. So we could give it normal distribution and say unit growth rate is the average, and then give it some sort of variation. We'll say 1% is fine. And it could go negative actually, so we don't need to truncate that distribution. But it's very, very highly unlikely to go negative there. Okay, but now we have some uncertainty here, and we could resample this. Probably don't need to resample it every day, but maybe we resample it every month. And again, similar to what we talked about before, is changes in growth usually are a little more stable over time. It usually it's not totally random from one month to the next, right? So I will put in some autocorrelation there and then refer to that value. Okay, then run the model. We're about out of time, so I just wanted to make mention of water conservation. That was one of the topics I said I was going to look at. But what you'll see here is that over time, there's a little bit more variability here. Maybe I didn't vary those growths enough. But if you increase the stochastic or the uncertainty in the population growth more, you see more spread here as you go forward into the future. Okay, so with this, we now have a pretty good representation of possibilities going forward in your future water demand. But I mentioned water conservation, so let me just talk about it for a bit. With water conservation, there's multiple ways of doing it. This model comes from our model library, and what it has is water conservation measures that are implemented on a per household basis. And so you would need to set up your demands a little bit different way. Mine is based on population. This one is based on housing. But it makes sense to set up for in terms of housing when you're looking at conservation, because a lot of times the water conservation measures that are being put in place are on a household basis. So, for example, you might have. Let me just open up this thing right here. Okay, so this shows us the rate at which we are installing new water conservation measures, and they don't all have to be the same type of measure. So some of them are low flow fixtures, like a low flow toilet, shower head, faucet, etc. And these are things where, for example, a city might put in some money to allow people to get rebates, for example, on some of these items. Another thing might be a media campaign that might cost money, but then also does have an impact on water conservation and other things, fixing leaks and so forth. So all of those things might conserve water in different ways, and they all have a cost associated with it. And so that's what this model does: is it looks at what is the rate at which we're adding these things, like how are people adding them, and also how long do they keep them, because there could be situations where people buy one and then they realize, I don't like this anymore, and they over time they might replace it. And so this model does account for that. It has a removal over time, as well as continually adding more. And so then you can determine how many fixtures per household, for example, and then calculate the total number of fixtures in the city that have been applied and figure out what approximate water conservation is occurring from this addition of these implementation or these measures. And then you end up with a conservation rate, which then can be subtracted from your total water demand. It's also important to note that some of the measures might be only affecting outdoor demand, and some of the others might only be impacting indoor water demand. So you'd need to apply the conservation measures appropriately for the different types of demand. Okay, so yeah, this could easily just be ported into our model, this water conservation plan. I'm not going to do it right now. We're out of time, but it's also, like I said, it's built in a little bit different way based on housing, so it would require a few more changes. But I just wanted to show that there to you. Okay, so with that, we now have a pretty good representation now of how to model water demands in a pretty simple case, but you can see how it's pretty easy to assemble the components that you might need. Reusing some of our existing models, for example, to build this model. All right. So thank you for joining. I do just want to make a quick note of um, what is coming up for the rest of this course. So let me go to our website and go to our webinars page. And I just wanted to make note of um, our upcoming lessons. Lesson 6 next week, we will have a guest speaker and be talking about pond and reservoir outflows. Also, we'll have a guest speaker in lesson 9. But importantly, I wanted to make note of another, if you're doing any kind of watershed hydrology type modeling, this is a nice model that was built by Nicholas Francoeur at Tech Resources, and I highly recommend that you register for this one. You can register by clicking here. All of these lessons do have links. You have to register for them individually, though, if you want to attend all of them. And you will also see that I changed the link to View Archive after I've given the lesson, in case you want to go back and look at the video or download any of the models. So thanks a lot for joining. I will hang around here for a bit to answer any questions that you might have, and hopefully I'll see you next week.